principle. But I don't really know the distribution this time, and so I'm relying totally on the mathematics of probability. But what I wish to say to you is that if we think of the problem in this fashion, right, we are assuming actually that there are no twins, which gives us prior knowledge. In the case where we're asking the probability of a shared birthday, given that there are twins, the probability goes to 1. Now, assuming they're born at the same day, not split over midnight, and assuming they both came to class and filled out the poll as well. So you could write down these probabilities and multiply them. And the second kind of probability where we have a prior expectation, this is sometimes called conditional probability, or in some sense, Bayesian probability. And we're going to cover that in the next 2 lectures. I say cover because it takes a long time to really cover things like a lifetime. Bayesian statistics is a deep and subtle thing, but we will go into it in the detail that we need for mathematical computer science. So already we have 2 scenarios. One where we have nothing known about the distribution, namely all we know is that there are students in the class and they have birthdays in some distribution. We don't know what that distribution is, but what we're doing is we're saying what's the probability they have the same birthday, and that's the simulation that we just did. In fact, not really a simulation, it's really a measurement we did. Let's see if we can predict that. The second one is given I have prior information, namely that there are twins. Can I show in that case that my probability goes up? In fact, it goes up to 1. Okay, so already some interesting and kind of unexpected results. So to think of this problem here, which is sometimes called the birthday paradox, we have everyone write their birthday down, and we assume there are k people in the room. There are 365 days in a year. We ask, what's the probability that 2 people share the same birthday? And we're not interested in using prior information, such as we know they're twins. And of course, I think some of you were surprised, or at least simulated surprise, and I really appreciate your playing along with this game in some sense. So to get kind of started here on our calculations, we could write the probability of a shared birthday. This is equal to 1 minus the probability of no shared birthday. And we will give you the tools to calculate this, but this turns out to have the following expression: 1 minus n times n minus 1 multiplied down to n minus k plus 1 over n to the k. Now, this is an interesting formula. We want to be in a position of deriving this. It's pretty good at calculating. Let's look at an example. Let's just set n, the number of days, to be 365. We'll ignore leap year for now. And famously, the lowest k, that is the lowest k in some sense, number of students for which this probability exceeds 1/2 is about 23 students, which is remarkably low. I was pretty sure we'd have collisions because we have 150 or so students. It looks like about 70 people participated in the poll. So doing some calculations here, it works out to this. If we write down a table with k here and the probability given that n equals 365, we can write this out. For 10 people, it's about 0.117. For 23, it crosses the threshold of chance, 0.507. For 41, it turns it to be 0.903. For 57, it turns it to be 0.9901. For 70, it goes up to 0.9992, getting very close to 1. So what's interesting here is using probabilities, we can make predictions. And if our assumptions are right about how things are distributed, this works really quite well, and the predictions can be super useful. So how do we build a foundation for thinking about these things? Well, the theory of probability can be thought of. I mean, I framed this as a bet, like, will you take a bet with me? So the theory of probability has actually always been associated with gambling. And many accessible examples, often ones that students enjoy, are associated with this activity, namely gambling. And this will also make you a better gambler, but I would appreciate it if you would not call up your parents and say that I'm teaching you how to gamble, because there could be all sorts of consequences of that. So don't tell your parents we're teaching you the theory of gambling, but that's basically what a lot of probability is. So you need to be familiar with the tools of the trade here, which are pretty cool. So one of the things we use in these examples is what's called a fair coin. You have a coin, you toss it, you get heads or tails. if you have a die, so singular die, plural dice, if the set of outcomes is 1 through 6, and you roll it and you get one particular outcome there. So that's pretty cool. Now, one example that I won't develop in detail, but I will talk about a little bit because many of you have been asking about bioinformatics classes, or you've been asking about my class next semester. So a lot of things happen that are driven by probability in biology and in computer science. So for example, if you're looking at DNA, which has 4 phosphonucleotide that can happen A, C, G, and T, you can imagine rolling a 4-sided die, a tetrahedron, so to speak, and getting one of 4 letters back. If you're designing proteins, there are 20 naturally occurring proteinogenic amino acids like alanine, cysteine, tryptophan, tyrosine in this case here. And you can imagine tossing a 20-sided die, which would give you, a randomly chosen amino acid. So these things come up in a lot of contexts. Again, not just gambling, but gambling is kind of a big one. So we always use the term WEP with equal probability because in our models, unless we tell you otherwise, if you toss a coin or roll a die, we assume that the outcomes can appear with equal probability. And a shuffled deck of cards means any ordering of the cards is equally likely. So how do we actually do some of these computations? I mean, it's nice to have these tools. These are typically built on various combinatorial tools, such as combinations and permutations. And these are actually covered in the Math 1 curriculum in high school Common Core. Many of you have seen them, you probably use them. But in my experience, it's good to review these, and there are a few people maybe who need a refresher in these. So I also don't want to give a proof of the combinatorial identities, although those are in the lecture notes, but I will give you a hint of why these proofs should be true, but please look them up. They're very reasonable proofs that we might ask you to do. So let's review combinations and permutations, and those will come up. And in particular, I want to come back to our example here, that the reason that we have this combinatorial formula here, which I stated without proof here, the reason I stated this was that this comes from manipulations of essentially combinations and permutations. Like that's how we count things, basically. So, I mean, I'm kind of some sense of combinatoricist, so I can make this joke, but in mathematics, we like to joke that professors of combinatorics are professors of counting in some sense. Okay, so let's review combinations and permutations, then use them to calculate some things. And again, I'm giving you a flavor for how this works, and some of the details are in the lecture notes. Please take a look. All right, so let's review these permutations. So again, if you don't remember these, look at the notes. If you don't remember them from high school, look at the notes, and I'll give you a sort of decent basis of it for here. So we want to assume that we have n objects, and we're asking what's the number of ways to fill n ordered slots with those objects. Let me write that down. So the number of ways to fill n ordered is n times n minus 1 multiplied down but to 2 to 1 is equal to n factorial. That's sort of formula 1. Formula 2 is the number of ways. So now we want to consider, what if we wanted to fill a smaller number of slots, but we still have at our disposal n objects we can put in them. Right, the number of ways to fill a smaller number of slots, say k, but I'll let it be as big as n slots, ordered slots. Again, with the same objects, with n objects. This is n times n minus 1 multiplied down to n minus k plus 1, which can be written as n factorial over n minus k factorial. Now, how would you prove something like this? By induction. And this proof, which is given in the notes, but this proof is actually very similar to the induction proof on midterm 2, although I think the one on midterm 2 was quite a bit, somewhat easier. So you should be able to do this, take a look, but we're going to use these formulas now. Okay, now I want to make a contrast between permutations and combinations. So permutations, they care about order. So they care about different orders. Combinations, which I'll define below, combinations count subsets. And by the very phrasing of this, when as soon as I have sets, we know sets don't care about order. The ordering does not matter. So roughly speaking, in the context of something like scheme, we could think of permutations as something like counting, approximately like counting the number of lists, because lists care about order. And combinations as being approximately like counting the number of sets or subsets. Now, the analogy is not perfect because in neither case for combinatorics can there be duplicates. So of course, with sets, there can't be duplicates, but we're interested in lists with no duplicates either. But roughly speaking, if you understand that there are differences between sets and lists being mathematical sequences, and we exclude the list where we have duplicate elements, although we can have different orders, we can understand that there could be a lot of different lists corresponding to the same set because we care about orders. So permutations care about different orders, combinations, the order doesn't matter. And this will be crucial for some derivations we'll be doing. Again, this is review, but let me now tell you how we think of combinations. I'll write that down here. So we have a notation for this. I'm going to say let this strange beast here, this is pronounced n choose k, be the number of different ways, different subsets with k elements out of a set with n elements. And again, this is pronounced n choose k. And I'll give you the formula and we'll do some intuition behind this. N choose k turns out to be equal to n times n minus 1 multiplied down to n minus k plus 1 over k factorial, which can be simplified or written as n factorial over k factorial times n minus k factorial. So let's get some intuition for why this equation might be true. Why this number might be true. Again, the proof is in the notes, but I'd like to give you some way of thinking about why this might be true and give you sort of a sketch of the argument or proof. So the way we can think about this sort of is as follows. So we have a big set here. And by the way, in this case, we're always talking about finite discrete sets. Very happy place for discrete mathematics and discrete mathematicians. So we have this big set of things. This big set has n different elements in it. And what we imagine doing is we imagine choosing a set that has k elements in it. And let's say in this case, k is like 5. So how many ways can we do that? In other words, I'll pick another one. We could pick another set here that has k elements and it has 5 different elements. But we also can have sets that overlap and so forth. So the number of different subsets, each with k elements, that's all drawn from this set, it depends on two things. It depends on which choice of the k elements. And we have to make sure we don't care about the order. So if I choose this set of k elements, it doesn't matter what order I choose them in, right? So therefore, we can kind of relate combinations and permutations. So one way to think about this is as follows. Look at the picture here. Why should this equation be true? Well, first we choose a subset. That's the subset here. And then we order its elements in a row to fill k ordered slots with the elements from the set with different objects, right? Then distinct choices of a subset and an ordering thereof will end up as distinct orderings. So therefore we can sort of derive this formula as follows. So let's think of this. By definition, n choose k. This is I'll just write shorthand here. This is a number of different subsets of size k. So in our picture here, it's the number of different circles we can draw. Keep in mind, these circles could also overlap. They can share elements. Now, for each one of these, it has k elements. So there are going to be k factorial ways of ordering it. So we can imagine taking this and multiplying it by k factorial. Why k factorial? This is the number of orderings for a set of size k. And this is simply equal to n times n minus 1 down to n minus k plus 1. Why? Well, to see that, look at our derivation here. Because this beast here, this is the number of ways to fill k, which is less than n, ordered slots. So a way to think about this is that basically we take the number of ways to fill k ordered slots, which we know is either the definition from permutations or we proved it by induction. And then what we say is, hey, but we don't care about ordering. Let's sort of mod out, like think of modulo, mod out by the ordering. We divide that by the number of orderings, namely k factorial, and then we get this quantity here, which we want to define as the number of different subsets, which don't care about order, with k elements from a set with n elements. So at any rate, proofs are in the notes. You should be able to do these proofs, especially after looking at them. But I wanted to give you some intuition for the proof methodology, induction here, and the proof argument here, which builds combinations upon permutations. Okay. Now we could spend more time on the proofs, and if you have questions on that, I'm happy to come back to it. But what I'd like to do is use some formulas like this to calculate some simple probabilities in order to give you a flavor of the kind of things we'll be exploring and their power, again, in the context of gambling. Okay. Now, let me give you an example of some questions and answers that we can sort of address with probability. So initially, this will be an illustration. I don't expect you to understand exactly how to get it until a little later in this lecture, or perhaps after you read the lecture notes. But I want you to see the way that probabilists think about this and the way the problem is approached and potentially the power of the problem. So in this context, I'm going to look at a card problem, and I'm going to start with a shuffled deck of 52 cards. And I want to distribute these, all 52 cards, to 4 players. So 13 cards each, which is fine. So I'm going to consider a running example of 2 questions. The first question is, hey, what's the probability that each player gets an ace? Second question builds on that, is that assume that you're a player. Let me call you player 1. What's the probability of the following? Suppose you're a player, and suppose you get a single ace. What then is the probability now that each player gets an ace? So what's the probability that each player an ace, given that player 1 got one ace. Let's just see how we can work that out with our newfound refresher in combinatorics and some definitions of probability. So I'm going to try to derive this, but let me give you the intuition for why such a thing should be true. Let's look at one. So the argument goes as follows. If any ordering of the cards is equally likely, then any position of the 4 aces in the deck is also equally likely. So by that reasoning, there are 52 choose 4 possibilities for the positions or slots for the 4 aces. So that's sort of our universe of possibilities. Now, so that'll be like the denominator of a probability. Now, out of these, the number of positions that give each player an ace is 13 to the 4, right? So number of positions giving each player an ace is 13 to the 4. All right. So let's just pause there. And let me ask you if this statement makes sense to you. And if not, we'll go into some detail. Do you see why the number of positions that give each player an ace, number of all possibilities, is 13 to the 4? And if you don't, please ask me a question.
Yeah, I don't understand. I see the 13 maybe is 52 divided by 4, but other than that, I'm not quite sure.
Yeah, no, great question. I mean, this can be counterintuitive, so I'm glad you asked. So basically, the idea is that what we want to do is we want to imagine that, it doesn't matter how we distribute the cards, but let's assume that player 1 gets 13 cards like this, say in a row. So it's pretty natural that the ace is going to be somewhere in here, and there are 13 possible places for that ace to go. And that's player 1. Now let's look at player 2. So player 2 also has 13 cards, and if they're going to get an ace, it can go anywhere too. So that also goes from 1 to 13. And we don't know where the ace is, but it's a position like this. So for 2 players, the places where the ace can go, there are 13 choices here and 13 choices there. And so basically the set of possibilities is the Cartesian product of the set 1 through 13 with itself. So 13 possibilities for the ace here, 13 possibilities for the ace there. That gives you 13 squared, and that gets you up to 13 to the 4th when you have 4 of them. Does that make sense? Do you buy that argument?
Yeah, thank you.
Yeah, great question. So therefore, the answer to question 1 is 13 to the 4 over 52 choose 4. And this turns out, when you calculate, to be approximately 0.105. Okay. And I'm going to revisit this proof a little later because I'd like to give you a proof that has more of a recipe. Like I gave you a mathematical argument, but how do you come up with these, right? How do you formulate these arguments? So we'll get to that in a minute. But let's build on this and try to answer question 2. So after you have a single ace, the probability of everyone getting an ace has to go up, right? Because there are a lot of possible worlds in which you didn't have any aces at all. And you ruled those out by having a single ace. So the previous answer, by which I mean the answer to number 1 here, this needs to be revised. In other words, we need to divide the previous answer by the probability that you, player 1, get a single ace. So the probability that you, by which I mean player 1, get 1 ace. We're going to calculate that now. But let me just point out that this probability, we essentially used it here. That's the thing we wanted to have given. That's why we're dividing in a minute. So what's the probability that you get a single ace? So that's something like 13, because it's going to go in your hand somewhere. Now times 39, choose 3. Why 39? Because 39 is 52 minus 13. That's where all the other things go, divided by the orderings. 52, choose 4. So this quantity is the probability that you get a single ace. It actually works to be pretty high, about 0.44. So you almost have even probability of getting a single ace. So we have to take this probability here for 1 and divide it by this. And kind of fortuitously for the calculation, this very big number, 52 choose 4, appears in the numerator and denominator, and so therefore it cancels out. And so the answer becomes 13 to the 4th over 13 times 39 choose 3 multiplied, and this is equal to 0.24 approximately. So this is an interesting situation where we have the probabilities evolving based on information. So when we don't know anything about who gets an ace, the probability that each player gets an ace is about 10%, 10.5%. But if you, player 1, know that you have an ace, then the probability that each player gets exactly 1 ace goes up by 0.24, and we can calculate that probability. Again, given that we've shuffled the deck accurately. Okay. So this is a lot about how probabilists and combinatorics professors and students think about probability. It's a sound argument. And by the way, this is, again, covered in the lecture notes. You can take a look at it in some more detail. But I'd like to give you, or at least start giving you kind of a recipe for these kind of formulas, proving these kind of things and calculating them, that is a little more mechanical. It's not quite as quick, but a little more mechanical. And I think that's going to be a nice way, and it can also prevent you from getting sort of unstuck. So let me show you what that looks like. We'll use that repeatedly in this course here. So we want to prove or argue our derivation for number 1 again. So we want to calculate this again. We had some good discussion about it. Why should this be true? How can we argue that? What's a general recipe? How can we solve these problems in general? All right. So basically, I want to consider a concept of an outcome. So we'll define an outcome a little more rigorously next lecture, but for our purposes here, an outcome is some ordering of the 52 cards. So I take the cards and I shuffle them, right? I shuffle them and I'm going to distribute them out. So I'm going to assume that an outcome is one of those orderings that determines everything. And of course, I'm going to assume in this case that every ordering is equally probable. So an outcome is an ordering of the 52 cards, and these occur with equal probability, WEP. Okay, new terminology. Okay, so given that there are 52 factorial equally likely outcomes. Right, that's the number of orderings. Now, as before, let's go back to our example here. We want to basically just rederive our 13 to the 4. The exercise I did with your colleague who had the question here was actually exactly the right argument. I'm just going to repeat that briefly. We have 13 to the 4 because we let the first 13 cards go to the first player, the second 13 cards goes to the second player, and so forth. So therefore, by our argument here, there exists 13 to the 4 possibilities to choose these 4 slots for the aces. So since we already basically proved that rigorously, I'm just going to write that down. So we have, there exist 13 to the 4 possibilities to choose these 4 slots for the aces. Now, if I have 4 slots for the aces, let's go back to our picture here. I mean, I'll draw one more down here. This is a slide here, just 3 aces here. I haven't said what aces go where. So I have to consider all possible orderings. For example, I could have spades, diamonds, clubs, or I could have clubs, spades, hearts, right? I can have all these different things in those places. So I have to basically mod out or correct for the number of orderings. So the number of choices to fill these 4 positions with 4 different aces is obviously 4 factorial. So I have to take that into account. So the number of choices to fill these 4 positions with 4 different aces is 4 factorial. Now, the other thing we have to do is we have to treat all the other cards. So there are lots of other cards that we haven't thought about. So we have to order the rest of the cards in 48 factorial different ways. Rest of cards. And there can be 48 factorial different ways to do that. And by this calculation, we come up with the following. And I'm going to write it down, and then I'm going to justify this. So probability we get here is 13 to the 4 times 4 factorial times 48 factorial over 52 factorial, which again equals approximately 0.105. So again, I want to come back to our picture here of why this makes sense. So again, we have a space of all possible outcomes, which I'm going to call S. So outcomes, this is some set S. Now, a subset of those outcomes called E correspond to the desired event. Namely, the desired event that we're calculating is that every player gets an ace. So E for event, S space of all outcomes. And it's a subset of this because they're outcomes in some sense. Now, everything here is finite, everything here is discrete. So the probability of the event E, and I'll annotate by event, that's the term you'll hear, event E, is simply equal to the size of E over the size of S, which reduces our problem to one of counting. So again, remember our situation, if you want like algebra, is that an event E is a subset of the outcomes S. Event, outcomes. So now our equation starts to make sense for our calculation. The number of all possible outcomes, as we already said, is 52 factorial. 13 to the 4, where does that come from? That's the number of possibilities to choose the 4 slots for the aces. 4 factorial, that's the number of ways to permute the aces to fit into those 4 slots. 48 factorial, that's the way that we order the rest of the cards, i.e. in 48 factorial different ways. So this is the size of our event in the numerator. This is the size of our total space of outcomes here. And so this is a fairly universal recipe for calculating probabilities. And it works particularly well in the discrete and finite case because the sizes of these are finite numbers. This will be equal to something like m over n. And we just calculate these using combinatorics and we divide them. Now, I should mention that a lot of what we're doing with probability also generalizes to continuous probability, but we need to think about that a little more carefully. There we'd be looking at the area of E versus the area of S or something like that. And I'll do a little more of that next time. Okay. So this is our framework for computing things about probabilities in the case of cards. Now, maybe this all makes sense, or maybe this is like, oh, that's kind of complicated. So I want to let you in on the fact that actually the history of probability is one of people finding things complicated and getting it wrong. And it's good to know some of this history because we can make really good questions about it that we can study as mathematicians or even give as problems. So we know that gambling dates back probably thousands of years. The Babylonians gambled, for example, as far as we can tell. But the birth of modern probability is thought to be around 1654. And it's a letter from a Flemish aristocrat and a notorious drunkard and gambler called the Chevalier de Marais. And he sent a letter to his friend Blaise Pascal, famous for Pascal's triangle, At that time, mathematicians kind of did a lot of other things. You could write them with your math questions. And he was really interested in gambling. So he asked Pascal for some help with gambling. So he used a term called even money. That's a 50-50 bet. So it's not like the bet I did before where I bet you a penny to your $10 or vice versa, your $10 to my penny. This is a 50-50 bet is like, if I win the bet, I get $1, you win the bet, you get $1. So this is written in fairly old, French, but translated to something like this. And we'll write some runes, some math up to summarize this, but let me just read it to you. So, dear Blaze, I didn't say dear Blaze, but I used to bet even money that I would get at least 1 6 in 4 rolls of a fair die. In other words, 4 6 equals 2/3. And clearly I had an advantage, and indeed I was making money. Now I try to bet even money that within 24 rolls of 2 dice, I get at least 1 double 6. This appears to have the same advantage because 24 over 6 squared equals 24 over 36 equals 2/3. But now I'm losing money. Why? What's going on? So this is pretty weird, right? So let's write that out so we can understand what he said. So writing that out mathematically, even money, he bets that if he rolls that more than, he'll roll at least 1 6 in 4 rolls with a single die. Remember, die is singular, dice is plural. So he's betting even money that he will roll at least 1 6 if he rolls the die at least 4 times. And he claims the probability of winning is 4 6, which is equal to 2/3. I put a star here for reasons that you'll see. And let's just annotate this by he's winning. He's winning money. But then he generalizes the game and he bets even money that he gets at least 1 double 6, which I'll denote by 6 6, within 24 rolls of 2 dice. Remember, singular and plural. And he claims to have what he calls the same advantage. And he claims that what he'll get here is 24 divided by 6 squared, which is equal to 24 over 36, which is equal to 2/3. But now he's losing money, hand over fist. So what is going on here? I mean, he's asking Blaise Pascal, he's like, I don't understand it. I've calculated the probabilities. I should be doing the same. Roll 1 6 and 4 rolls of a single die. It's 2/3. I'll take 2 dice. I'll roll them 24 times. The probability of getting at least 1 double 6 should be 24 over 36. Same probability, but I'm losing. What's happening? Is probability broken? Is something bad happen here? Now, this was an interesting question to Pascal. So he ended up talking to another now famous mathematician called Pierre de Fermat. And I wouldn't say that Pascal couldn't have figured it out, but he certainly brought Fermat into the loop. And between the two of them, Pascal and Fermat figured out what was going on. Does anyone see what the problem is here with Chevalier de Marais' reasoning? What's going on with this? Any ideas?
All the 6s they're not exclusive events, so you can't just add them.
Yeah. I think that's basically what the problem is here. So you've come to a mechanistic explanation of the misunderstanding. And you're totally right. What Fermat did, because we're probabilities being born at this point, is he basically first wanted to just show that Marais was wrong. De Marais was wrong. And basically what he wanted to do is show small t by what we call a reductio ad absurdum, namely a contradiction. He wanted to show the proof technique was wrong, which is, by the way, exactly what you all said, right? Can't do it. So how do you show that? Well, what he reasoned is the following, in some sense. What he did to reason about this is he said, well, what if in the first game, this one here, you were to roll, the number of rolls was 7 instead of 6? So I'll put in contradiction here. What if we had 7 roles? So exactly as my colleagues said a minute ago, in that case, we would get the absurd probability. The probability is equal to 7/6 of winning, which is greater than 1, which is not cool. So Fermat showed, immediately after some thought that the proof technique that he was using, the calculation technique, was wrong, which is exactly what you all are saying. So again, a reductio ad absurdum is we try to get a proof by contradiction by proving something absurd, so the technique is wrong. So I just want to make a couple of comments here. I mean, both these probabilities that are starred are wrong. And in the notes, and I'll discuss it a little bit next time too, the remarkable thing about this is if you calculate the probabilities are correct, you can do 2 things. One, you'll feel intense personal satisfaction at having gotten the probabilities correct. But second, as a historian or a computational archaeologist, so to speak, you will be able to prove mathematically that my assertion that Desmarais was an incredible, notorious gambler that gambled all the time was actually correct. So give some thought about how the mathematics could actually prove that, given the limited information that I've told you. Finally, let's do a little mathematical culture here. Fermat's a pretty famous guy. You've actually already encountered him in problem set 2, Fermat's little theorem, which we actually used some there in problem set 2. One thing you might not know is that how he argued for this. So when he did this, he wrote a letter to his friend, de Bessy, right? And what he wrote here was, et cette proposition est généralement vraie en toute progression et tout nombre première, de quoi je vous envoie la démonstration si je n'ai pas le droit d'être trop long. Or in English, and this proposition is generally true for all sequences or progressions and for all prime numbers, the proof of which I would send to you if I were not afraid it would be too long. So this isn't exactly the proof standard we use in our class today. So no proof, but a claim that there exists a proof. Quite a bit later, right, nearly 100 years later, Euler gave the first published proof of this, and it looks like Leibniz and others gave proofs of this that were rigorous. But this is sort of amusing. If you'd like to look at the history of this, you can also look at the history of Fermat's comments on his so-called last theorem, which was proved by Andrew Wiles about 380 years later, where he had a different but similar comment. So anyhow, story of Fermat, story of Desmarais involving Blaise Pascal, and indeed, these probabilities are wrong, and we can calculate them correctly using the tools that we've already seen. Okay. Now, at this point, I would really like to give you an example that didn't involve gambling or relate to gambling. So these really are application sketches, not really examples, but they come from bioinformatics. Some of you have asked some questions about that, and they're pretty cool. So I want to just sort of allude to them a little bit. So if you're doing computational biology and bioinformatics, you run against probabilities. So some of the tasks you do are aligning sequences from genomes, say, reconstructing family trees, genetic information, predicting genes. So basically in science these days, whenever you are asking questions from data, you're going to run into probability and statistics. And these happen a lot in the context of biology. So one example of doing this is the case where you have these sequences, which are based on 4 different nucleotides, and evolutionary changes can be thought of as differences in these strings. So given 2 sequences, are they similar enough to conclude they had a common ancestor? So 2 statistical problems. What's the best way to align these sequences, even if there are gaps or changes? And can you decide whether the similarity of the alignment is significant, whether these really are related in some sense? Very important forensics as well as in paleontology, biology, microbiology, evolution, and so forth. So sequence alignment of DNA can be thought of like this. You have 2 strings, if you will, and the strings can be set up like this, and you're interested in how do they match up. So again, you have 2 different DNA sequences, you have matches at certain positions. when is it sufficient to conclude that the two sequences are actually related evolutionarily? Again, probabilities can help us answer these questions, and we have all these ingredients that we want to cover some of, but not all of today: random variables, probability distributions, independence, and so forth. And again, as I've alluded, there are really two kinds of flavors of probabilistic reasoning. I won't go into the more or less religious arguments between these, but frequentist probabilities and probabilities that take into account priors. The phrasing here, this is written by a French TA, so that they fair to sport. But again, we have analogies in the biological world that are going to correspond to our discrete random systems. We not only can roll dice or toss coins, but we can imagine we have random processes that are randomly mutating sequences of nucleotides, such as ACGT, and we are thinking about amino acids and changes in proteins between 20 different possible amino acids. So here we have a 4-sided die, here we have a 20-sided die. And of course, to actually do our calculations, we need sort of a set of rules to do these that are a lot like things you've seen in set theory, perhaps. We want to find ways of knowing that these formula, which relate different kinds of probabilities to other probabilities, are true. How can we derive these for our cases? We'll talk a little bit about that in the next couple of lectures. So that's kind of where we're going with this. We want to have rules like this that look a little dry when written on the paper, but actually let you calculate about any system that has a probabilistic nature or basis. And we're going to do some of that to see why this makes sense. Okay. Now, here's one more sort of biological example, and go back to something we could actually calculate. So I can't calculate anything given what we know about DNA sequences, but I can do some other things. So here's the question, just to kind of think about outcomes and probabilities calculations. Suppose we have a family with 4 children. What's the probability that there's a 2-to-2 split between boys and girls? So we'll do some calculations, or at least set them up in a minute. But what do you think this probability would be? Any ideas? See some answers in the chat. There's a suggestion of 1/4. Any other ideas? 1/16. Let's see. Any other thoughts? No other calculations or guesses? Hypotheses? One half? 1/4 again. What if I told you about that all of these are actually wrong? 1/5, okay, that's another one, okay. So this is a somewhat surprisingly subtle example. So these are actually all incorrect, but thank you for playing. Let's discuss it a little bit. So one common answer that is sort of, that's not right is 1/5. And the reason that 1/5 might seem kind of natural is that, there are 5 possibilities for the number of boys, and girls. Turns out they're not equally likely. So that's why we don't have 1/5. Another common answer is close to 1. That's the most balanced possibility. It represents, mistaken belief that symmetry and probability should very likely result in symmetry in the outcomes. But actually, the answer of a 2-to-2 split, probably 2-to-2 split, is equal to 3/8. So maybe I've been able to convince you now that we have some reason to take these calculations seriously, not as obvious. So let's try to figure out why this should be. So again, let's look at our cases here. We have a set of outcomes. We have an event that we want to happen. And again, if the size of the event set is, say, M, and the size of the outcome set is, say, N, then the probability is just M over N. Right, that's sort of our calculation here. So how do we think about this? So again, let's go to a very basic example. Suppose we have a fair die, and it has 6 outcomes, 1 through 4, and take E to be an event which is 2, 4, and 6. Then the probability of this event is equal to 1/2, because there's 6 possible outcomes and the size of E is 3. So note what I've done here is that probability is actually based on set theory. So informally, probability is equal to set theory plus some probability measure satisfying certain conditions, and or axioms, and we'll talk about that next time. So this is our example here. How would we go about thinking of our case in this particular example? So I should also mention that in the case of die or dice, it's very difficult to attach a meaning to the probability of an event if we just roll the die a single time or a few times. The most straightforward interpretation of probability is that for a very large number of rolls, about half the outcomes will be even, as I've shown here. And this requires, at the very least, the notion of a limit in order to make this rigorous. Okay, so let's go back to our case of boys and girls in a family and see how we might calculate that. I'll give you the basis for doing this. So we have outcomes which we will assume are equally likely. And one outcome might be something like this. So all boys. Another might be boy, 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 girl, boy, boy, girl, boy, 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 girl, girl. We also have, I have boy, girl, boy, boy, etc. And we might have girl, boy, boy, boy. These might be the given in birth order, for example. So we have all these different possibilities for how to do this. And notice that in terms of counting things, these are the same counts for the split. So if you fill out this table, which there was intuition here, right? There are 16 things here that you have to compute. But if you fill out this table, you'll find, all right, et cetera, that the probability of a 2-to-2 split is equal to 6/16, which is equal to 3/8, if they're all equally likely. What about the probability of a 4-to-0 split? What's this equal to? Any ideas? 0.5 to the 4th. What does that work out to be? 1/8. Thank you. That's 1/8. Good. What about the probability of a 1-to-3 or 3-to-1 split? What's that equal to? I'm putting them together because I don't care if it's, yeah. I don't get 3/8 for that. I get 1/2 for that. That's good. That one's 1/2. Good. All right. So now we're calculating together. So a little bit subtle when you think about this. It really does come up. I mean, in real life, you know, my kids are in college now, but when they were younger, they raised chickens, and you know, now in Chapel Hill they have these strict ordinances. You can only have hens, and you can only have 9 of them at most. So we got some chickens for them at one point that they raised and were great pets. And these chickens came, you know, unsexed. They could have been male or female. But of course, it's biology. So we were kind of surprised when there were only 2 females and the rest were males. But that certainly is a fairly likely outcome when you just do these choices. Okay. Now, in the remaining time, I want to make some connections here to science in general. And so in order to do that, I want to just show some stuff on my device here about the role of probability. And then we'll do some more details. So we'll be somewhat more axiomatic as we talk about this on Wednesday, because we want to derive these rules of probability, and we want to think carefully about how do we actually do these calculations. But I did want to sort of indicate to you, where these things come up in the wider world of science and computation, which I know some of you are considering as you go ahead. So I'm going to share my screen from the tablet, and we'll take a look over here. All right. So what's the context of what I'm talking about here? So a lot of you have asked questions about my spring class. So this is computational biology with some focus on virology here. So one very interesting question is, well, where's the mathematics? Where's the computer science in here? Obviously, there are algorithms to design these drugs and model them in some sense. But one point of connection between this kind of work and the work that we do in discrete mathematics and mathematical computer science is actually probability. So of course, it's there for the optimization algorithms, there for the modeling in some sense, but probability comes up all over the place in biology and chemistry. Let's just look at an example here. I'll use some to think about that we can think about. So this is an example not for COVID, but it's for another virus, namely HIV, which you've heard of. And one of the things that comes up immediately is that if you just take a genomic approach to this, then you know something about the parts list for how pieces of the virus are made, but you don't know its 3D molecular architecture, which makes it difficult to design interventions. So in some sense, you want a structural picture, a geometric picture of the 3D architecture, and this is the basis of what's called structural biology, by which we visualize the shapes of these molecules based on detailed experimental measurements. Now, one of the things that's nice about this field is that everyone deposits their data, and you can see these models, and they have these beautiful pictures like this. But in fact, all these molecules are flexible. And in fact, they don't just assume one shape. They go through motions and changes, and they form a distribution of structures over some space. Now, this has something that can be nicely understood in terms of computer science. So if you just want the most likely state, that corresponds biophysically to the lowest energy state. This is a maximum likelihood calculation, which obviously is based on things like probabilities. But you also might like to talk about all of the states at once that are reachable. And this is some kind of average or integral over the set of shapes. So this is sort of a more sort of Bayesian approach in some sense. And so as soon as you start trying to interpret this biological data in terms of talking about not just one shape, but a family of shapes that represents a molecular machine that's changing and flexing and doing all these things so it can do its job, then you're immediately talking about the language of probability. And in fact, if you've taken a chemistry or physics class, you move back and forth between the probabilities we use in this class and energies in physics and in chemistry using something called the Boltzmann distribution, which is just an exponential distribution. So what I want to indicate to you is that in some sense, when we are computing quantities of interest, like how well does an intervention for COVID neutralize or bind to a virus, we're doing calculations over these distributions, which often are discrete. And we're finding ways to visualize these distributions, namely, what do these set of different probabilities over different states look like? And so really the only point that I want to make here is that if you are interested in the interplay between probability computation and the life sciences, then any of the courses that you all have mentioned that deal with these issues in computer science, such as the genomics class 260, Alberto's class 290, my class 590, they all are looking at that interplay, and you'll find probabilities coming up a lot. So even if you weren't interested a priori in probabilities, which are incredibly useful in computer science and discrete mathematics, they're super important in science, particularly biology, chemistry, and biomedical science as well. And I'm trying to either refresh or teach you about probabilities in such a way that it will be useful even in the case where we generalize beyond discrete systems, although in this class, our main emphasis is discrete systems. Anyhow, if you're interested more in more about this, and certainly further than we'll go in this class, you can grab me and we can talk about it at office hours. But I did want to mention this connection, and it sort of is a way that this ties into other things that we'll be talking about in this class. And I also want to reassure you that in this class, we will use these as some examples, but we won't be asking you anything about nucleotide sequences, protein sequences, biology. Those won't be examples of interest to us, but the underlying machinery will possibly be quite interesting to us. That having been said, I think that's the examples that I want to do today. So on Tuesday, we'll do more probability, probably stepping in to introduce conditional probability to some extent and do some calculations. And we'll basically have 4 classes that will do probability for us, 3 by me and 1 by Alex and Abe, which will be